In this video, we will look at limits involving infinity. If f increases or decreases without bounds as x nears a, then we have the limit as x approaches a of f of x equals infinity or negative infinity. If f approaches a number L as x increases or decreases without bounds, then we would have the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. We can use these limits to prove the existence of asymptotes. Let's take a look at the vertical asymptote first. We have a definition. A line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit as x approaches a from the right of f of x is positive or negative infinity, or the limit as x approaches a from the left of f of x is equal to positive or negative infinity. Let's take a look at an example. Let's see if we can find all the vertical asymptotes of the function f of x is equal to x plus 1 over x squared minus 1. And let's see if we can justify our answer. All right, so let's first take a look a little bit more closely at this function. So we have f of x is equal to x plus 1 over, we said, x squared minus 1. So let's take a deeper look at that. That really is the same thing as saying x plus 1 over x minus 1, x plus 1, right? Factoring the denominator. And we can see that our denominator is 0 at x equals positive and negative 1. So let's see what might be happening at 1 and negative 1. So let's take a look at negative 1 first. All right, and let's write the limit as x approaches negative 1 of our function, x plus 1 over x minus 1, x plus 1. Now, of course, if we plug in negative 1 right away, we're going to get that scenario where we have 0 over 0, right? It's indeterminate. So we're going to need to do a little something extra, right, to find our limit. So, of course, after we factored, we can easily see that my x plus 1s are going to cancel out right there, right? And this is going to be equal to the limit as x approaches negative 1 of 1 over x minus 1. All right, and from here, of course, we can go ahead and plug that in, and we get 1 over negative 1 minus 1, and that is equal to 1 over negative 2. So we can see here that the limit exists. We have a finite number, and so there's going to be no vertical asymptote at x equals negative 1. So no vertical asymptote at x equals negative 1. All right, so we've tested what's happening at x equals negative 1. Let's see if we can figure out what is happening at x equals positive 1. All right, so let's take a look. All right, we've got the limit as x approaches 1 of x plus 1 over x minus 1, x plus 1. All right. Again, let's go ahead and cancel out those x plus 1 terms. And we've got the limit as x approaches 1 of 1 over x minus 1. All right, now again, if we were to plug just 1 in right there, we would get 1 divided by 0. So let's think in terms of our one-sided limits that I spoke about in a previous video. Let's see what happens as we are approaching 1 from the right-hand side. So we are going to write this as 1 over 0, but as I'm approaching from the right-hand side. And so as I'm approaching 1 divided by a really tiny number, we would say from the right is going to give me positive infinity. All right, and let's repeat that idea, except this time from the left. So we have the limit as x approaches 1 from the left, of course, is now just 1 over x minus 1. And now approaching from the left-hand side, 1 over, again, a really tiny negative number. This time we are going to get and say this is negative infinity. And so since our limit from the right is approaching infinity and our limit from the left is approaching negative infinity, we would say we have one vertical asymptote at x equals 1. All right, so let's shift gears for just a second. I think we've looked at an example showing that we can get infinity and found our vertical asymptotes. All right, but how do we handle things like the limit as our function x is approaching infinity? And that brings us next to our horizontal asymptote. So we say the function f of x has a horizontal asymptote at y equals L if and only if one of the limit as x approaches infinity or negative infinity of f of x exists and is equal to L. So let's take a look at an example. Let's see if we can find all the horizontal asymptotes of a function using the given limits. So let's see if we can find the limit as x approaches infinity and negative infinity of x squared minus 2x plus 4 over 3x squared minus 5. All right, so let's see if we can do this one. So limit as we approach infinity of x squared minus 2x plus 4 all over 3x squared minus 5. So my first gut instinct might be, okay, let's go ahead and just like plug in a really big number, that idea of infinity. So I have infinity squared minus 2 times infinity plus 4 over 3 times infinity squared minus 5. Okay, so what the heck would that actually mean, right? So if I try to square infinity here, I'd get a really big number, but then I need to subtract a really big number, and then all of that would be divided by another really big number. So as you can imagine, all right, that infinity minus infinity, or anytime we get infinity divided by infinity, it's one of those indeterminate forms. So we can't really know exactly what's happening, so we got to try some sort of other algebra, manipulation, try to actually answer this question, just like we've done before. So let's try the limit as x approaches infinity of our function x squared minus 2x plus 4 over 3x squared minus 5. So one gut instinct might be to factor, but I'm not really seeing anything good to factor necessarily for this one. So another technique you might use is trying to divide, or you can think of it as multiplying by a reciprocal. If I take this function and multiply it by the highest degree, I'm going to multiply by 1 over x squared, and I'm going to get the following. Again, it's a fraction. As long as I do the same thing top and bottom, we're good. So what do I have? The limit as x approaches infinity. And now once I multiply that all in, I'm going to get 1 minus 2 over x plus 4 over x squared, all divided by 3 minus 5 over x squared. All right, so now all that is simplified. Now I can think a little bit more about going ahead and plugging in infinity or plugging in a really big number. And so when I do that, let's see what happens. So I got 1. Then if I plug in infinity, 2 over infinity, right? 2 over a really big number is approaching 0, right? 4 over a really big number squared, again, is approaching 0. And same thing on the bottom here. And so what that leaves us is with Just the coefficients 1/3 right there. All right, and I can repeat this idea for the limit as x approaches negative infinity. All right, and we would get the same thing, 1/3. And so we say this function f of x equals x squared minus 2x plus 4 over 3x squared minus 5 has one horizontal asymptote at y equals 1/3. And so this may be familiar from pre-calculus, but we have some special cases for limits at infinity. And we say if the degree on top is bigger, so the limit as x approaches infinity of some rational expression, that's going to be positive or negative infinity. If the degrees are equal, so the limit as x approaches infinity of our rational function is going to be equal to our leading coefficient. And last but not least, if the degree on top is smaller, when we take the limit as x approaches infinity, we should get 0. And the last type of asymptote is the oblique or the slant asymptote. And we say this happens when the degree of the numerator of a rational function is 1 greater than the degree of the denominator. An oblique or slant asymptote is in the form of a line y equals mx plus b that the function approaches as x increases or decreases without bounds.